Okay, so we're going to think about lines just a little bit more before we do one last thing in terms of planes, or a couple last things in terms of planes. So now I want to find the vector and parametric equations of a line in R3. We're asked for vector and parametric because remember, in R3, I cannot do the general equation of a line. Now this line is going to pass through the origin and be orthogonal to vectors u and v. I remind you, orthogonal means perpendicular, so I have these two vectors that are perpendicular to my line. So I know that my vector equation for the line is going to be x, y, z is equal to some point plus t times some direction vector. So in other words, I need a point and a direction vector. It gives me the point. It says that it passes through the origin. Passing through the origin means that the point is the origin. So my point here, what I have is my point. My point is 0, 0, 0. And I have two orthogonal vectors. And I need then a direction vector. So the question is, how do I find a direction vector when what I have is two orthogonal vectors? Well, we're finally going to use the cross product. So if I were to draw this, this is my line. So then I have this one vector. We'll call it n1. And I have this other vector that we're going to say is sticking out of the line. So pretend that that's like sticking out of the paper here. So I have that, and I have, oh my gosh, I'm sorry, I'm so terrible at this. That. Oh my gosh, I hate drawing in 3 dimensions. Okay, well, pretend that you can see that. So we have that sticking out. So these are both orthogonal. And what I need is a vector that is parallel to my line. So I need this direction vector here. Well, if my line is orthogonal to both of those vectors, then my direction vector should also be orthogonal to both of those vectors. Will be orthogonal to both vectors. So how do I find a vector that is orthogonal to two given vectors? That's the cross product, when we're in R3 at least. So to find a vector orthogonal to two given vectors, use the cross product. So in other words, in this case, my direction vector D will be equal to U cross V, which is, remember, we set up our little determinant with the stars at the top for kind of like our trick for how to calculate. So that's 3, 5, -7, 1, 2, -1. We cofactor expand across the first row, not multiplying by the stars, pretending they're not there, to get these 2 by 2s, 5, -7, 2, -1. Cross out the second column, but remember we're now in a minus place, -3, -7, 1, -1. Then cross out the third column to get 3, 5, 1, 2. Which gives us these 2 by 2 determinants to calculate. So I have -5 plus 14, which gives me 9. -3 plus 7 times -1 gives me -4. And then 6 minus 5 gives me a 1. So that's my direction vector. My point is still 0, 0, 0. So my vector equation here is x, y, z is equal to 0, 0, 0 plus t times 9, -4, 1. I don't really need to write that 0, 0, 0. It doesn't add anything. So in other words, x, y, z is equal to t times 9, -4, 1. And then remember, my parametric equations follow directly from my vector equation. X is equal to 9t, y is equal to -4t, z is equal to t. So this is the vector, and this is parametric. And that's my final answer here. Ta-da! So we had to use the cross product because we needed to find a vector that was parallel to our line, and it was therefore orthogonal to the two orthogonal vectors.